Hi, welcome back to CS560. So from this lecture on, we are going to talk about the second type of advanced graph algorithms. So this type of algorithms solve this particular type of problems, which is single source shortest path problems. Okay, so a single source shortest path problem is a very common problem that we often use our cell phone or computers to solve a lot. So, for example, if you open the Google Map and wants to find the shortest possible routes from one place to another, from San Diego to Seattle, and it is essentially a shortest path problem that the backend algorithm of Google Map will solve it for you. So if we so for sure the Google Map, the server will represent the US map as some kind of graph data structures, and for example the adjacent intersections can be represented by the vertices in the graph, and the length of each segment of road can be represented by an edge in the graph. So it is a very typical problem. Say if I want to find the path from one place to another, and we can represent each intersection as a vertex in the graph, right? And we can represent a segment of road that connecting the two intersections as an edge. Okay? And of course, the length of the segments could be the weight, or more accurately speaking, because nowadays the Google Map or other map can estimate the travel time for you. So it's basically the estimated time of traveling at that moment to be the weight of the edges. Okay, so usually the graph is directed, right? Because we're trying to build a one-way direction from place A to place B. Okay, so that is the so-called daily usage of daily application of the shortest path problem. Okay, but more formally speaking, if you want to define the shortest path problem using the programming language terms or mathematical expressions, we should use the graph terms, like given a weighted directed graph with these vertices and edges, and of course with a weight function w, because now we care about the weights for each edge. So the shortest path problem is defined on a set of paths. So the weights of a path, and a path is defined by a series of vertices and the total of the segments, a total of all the constituent edges along that path. Okay, so the weights of that path is the sum of the weights of its constituent edges, of all the, that is to say, of all the, we just sum up all the weights of all the edges along the path, and that will give us the weights for that path. Okay, so this big sigma means we sum up all the weights along the path. Okay, so now we can first define the shortest path weight. Okay, so the shortest path weight is a scalar quantity. It's a number. Okay, we use delta to indicate this quantity, and this delta of u and v means that the starting point or the source point of the path is u and the destination is v. So the delta of u and v means the shortest path weight between of the path between u and v. Okay, it is the path that has the minimal sum of weights. Okay, so it's defined as this mathematical expression. So with two conditions. So the first condition is that if there is a path, so if the path indeed exists from U to V, or we say if V is reachable from U, right? So if that is possible, then the shortest path weight is the minimum value among all possible paths from U to V. Okay, so there could be multiple passes from one vertex to another one along the within the graph, but it's not necessarily that all passes would have the shortest weight. So we choose the path that has the shortest weights, that has the smallest weights or minimum weights, and then we use that minimal summation of weights as our shortest path weight, delta. So delta, just keep in mind that delta is a number, is a quantity, okay? And we will use that quantity delta a lot in the later definitions of the algorithms. Okay, so technically speaking, delta between U and V is the smallest number among all possible paths. So no path should have a smaller weight than the delta. Okay, so we say that a shortest path between U and V can be defined as any path that has the shortest path weight. So there could be more than one shortest path between U and V. There could be 2 or 3 or even more paths that have the same total sum of weights, which is the delta. So as long as the weight of the path equals the delta, then we say that it is a shortest path. So there could be multiple shortest paths. The shortest path problem that we talk about today is kind of related to the breadth first search algorithm, which is the elementary graph algorithm that we talk about on the first day of this chapter. So in BFS, we also say that it is able to find the shortest path between the source vertex to any vertex in the graph. Okay, but in that sense, in BFS, the shortest path it's defined on unweighted graphs. Okay, so you can think of BFS as a special case of a shortest path algorithm, because in BFS works on or at least the BFS that we talked about before worked on unweighted graphs. So each edge has, or all edges has the same weights. They are all unit lengths, or they have the weights of 1. Okay. So or to say it another way, the shortest paths in BFS are defined in terms of the number of edges. So we say vertex T is 2 edges away from the source vertex S. So this number 2 means the number or the count of edges, which is 1 and 2. Okay. So in the example we use here, the input weight is an unweighted graph. Okay, but now in the graphs that we talk about in this lecture today is about weighted graphs. So the shortest paths, the distances are not defined by the numbers of edges, but by the weights of the edges. So that is a major difference from the so-called shortest path in BFS. Okay, so in this lecture, all the graphs look like this way. So we all have weights associated to each edge. So there is a bunch of variants of the shortest path problem. So depending on the number of destinations and sources that we predefined. So we focus on one type, which is the single source shortest path problem. So this problem basically wants to find a shortest path from one given source to all the other vertices in the graph. Okay, so it is a problem that's given the source, we want to know the shortest path to all the other destinations possible. Okay, but essentially it's the same type of problem. We basically want to iterate over, to go through over all possible paths from one destination, from one source to one destination. Okay, but that if there are multiple destinations, then we need to do that computation for multiple times. It's simply speaking, it's that way. Okay, so the other variants are single destination, right? Single destination shortest path problem, which means that we care about just one destination. Okay, but we may be interested in multiple sources. And single pair, which means there's just one unique pair of destination and source. And all pairs. So all pairs shortest path problem, it basically includes all possible combinations of source and destinations. Okay, so a shortest path problem is a very typical problem that demonstrates some optimal substructure. So this term, optimal substructure, is a terminology that we used when we talk about dynamic programming and greedy algorithms, right? So it's basically about the fact that the shortest path, this original problem, can be decomposed into smaller problems. Okay, so in our case, a shortest path between two vertices must contain other shortest paths within it, right? So say if you take a segment within, so given the shortest path, and you take a segment on top of that shortest path, so that segment also itself must be a shortest path between some vertices within the path, right? So it indicates that dynamic programming or greedy algorithms might apply in this case. Okay. So the textbook actually uses a lemma to prove that the subpaths of a shortest path are themselves shortest paths. So it's a very recursive definition. So it's an interesting lemma. So if you are interested, you can go to the textbook to have a more detailed proof out of this for this lemma. So it basically says that given a graph, and we just use some path, letter P, to indicate the path, to indicate the shortest path from vertex V0 to Vk, and there could be a lot of other vertices along the way. Okay, so for any integer numbers that's between 0 and k, and we let the p subscript ij to indicate the segments, okay, from vertex I to vertex j. So that segment pij must also be the subpath. It must also be a shortest path from vj to vi. Okay, so if vj, I think it's a straightforward theorem, because if pij is not the shortest path, which means in theory it could be smaller, then that means the p is also not minimum, which violates our assumption. Okay, so that's the basic optimal substructure of shortest path problem, which is good to know. All right. So now let's talk about the negative weight problem, negative weight issues when we define the shortest path. So we allow the cases of negative weights because the edges, if we are not if it's not a distance problem, but for example, if we are using the graph to represent the transfer of money between banks, then maybe the negative number may have some special meaning, say that money is transferring out or back stuff. So negative weights are allowed in our setup of the problem. So the weights are not necessarily positive. Okay, so we allow the existence of negative weights. Okay, but we say that the graph should not contain negative weight cycles. Okay, so the shortest path delta, the shortest path weight delta for all the vertices in the graph will be well defined if and only if there's no negative weight cycles. So if there's one negative weight cycles that is reachable from the source, then the shortest path problem is not well defined. So we'll see later why. So it's basically because if there is such a negative weight cycle from S, then the shortest path could be smaller and smaller if you go through that cycles multiple times. Okay, so if in that case, if a negative weight cycles exists on some path from the source to the vertex, then we just say that the shortest path weight, the delta, is infinity. It is not defined. Okay, so in the next slide we'll see why this is the case. Okay, so for example, we use this input graph to show the cycles. Okay, basically a cycle means that means a loop in the graph. So the arrows, the edges point from C to D, and there's a edge that point back from D to C. Okay, so in this graph, there's only one path. If you look at the upper path, so there's only one path from vertex S to B. Okay, and there are infinitely many passes from S to C. Why this is the case? Because, for example, the single edge from S to C is one path, right? But we can also go from S to C and then to D and then back to C. That is one path as well, right? From SCDC, this series, so this sequence between the brackets, between the sharp brackets is also a path. But this is not the end. We can also go this infinitely, right? We can go from S to C to D to C and then to D to C again, which is SCDC, DC. So this is also a path. So as long as there is a cycle in it, then there are infinitely many passes from S to C. Okay? But since the cycle from C to D to C has a positive weight, right? Because the weight of CD is 6 and the weight of DC is -4. So the summation of one cycle is 6 plus -3, which is 3. Okay, so we can say it another way. If we go in that cycle from C to D to C, it'll cost us 3 in total. So 3 will be the total cost of going that cycle for one time. Okay, so that means if we go through that cycle for multiple times, the cost will increase. Okay, so the SCDC, this path with a lot of cycles is not the shortest path because the cost increases if we go through multiple times. Okay, so therefore the shortest path from S to C is just the edge. just the direct edge from S to C, but not including any cycles from C to D to C, okay? And another inference is that the shortest path from S to D is also S to C to D, a direct connection, but without any circles connect back to C and then to D. Okay, because the main reason is what we just said, because the cycle has a positive weight. Okay. Okay, but now this is not the case for this cycle from E to F and to E. Okay, if we look at it closely, the summation of all the weights within this cycle is negative, because 3 plus negative 6 is negative 3. So this cycle has a negative weight. So that means if we go through that cycle for one time, the total weight will decrease by 3. Okay? But in our definition, if we want to find the shortest path, then we want the lowest weight as possible, right? But that cycle will give us a chance to go into that cycle without stopping if our goal is to decrease the total weights. Okay? So in that case, there's no shortest path actually defined from S to E. Okay? Because if you say that the shortest path from SE is 2, then we just go through one cycle. Then that will give us 2 plus negative 3, which is negative 1, which is a shorter weight, which is smaller weight. So in that case, as long as there is a negative cycle in the graph, then the shortest path is not well defined. Okay, and that also applies to the vertex F and the vertex G, because along there from S to F, there's a path that includes the negative cycles, negative weight cycles, and from S to G, it also includes the negative weight edge, the negative weight cycles. So in general, when we talk about shortest paths in a graph, we are actually not considering the cycles. So a shortest path should never contain a negative weight cycle. Because if there is a negative weight cycle, then the shortest path cannot be defined. It is just infinity. And a shortest path should also not contain a positive weight cycle, right? Because if there is a positive weight cycle, then we can always remove that cycle so that get an even smaller total sum of weights, right? So we assume that when we are using algorithms to find shortest path within a graph, then the resulting shortest paths should have no cycles in them, because they are simple passes. So we assume that they are simple passes that we are finding. So in this case, we have, in example here, we have a positive weight cycle from A to B. Then the shortest path from S to A is just SA, and then there shouldn't be a cycle in it. And from S to B is just SA and then A to B, and there shouldn't be a B to A and then A to B again, because the positive cycles we should not include it, and we just consider the simple path. Okay, so the last issue is how we represent the shortest path. So we have done so before when we talk about the results of BFS, right? We use a BFS tree, breadth first search tree, to indicate the results of a breadth first search. Okay, so in detail, we use a pi attribute to indicate the parent node of each vertex, right? Or the parent predecessor, the predecessor vertex for each vertex in the graph. Okay, so that's v dot pi either points to another vertex or to none if there's no parent. Okay, So using these parents, these pi attributes, we can get a chain of predecessors of a vertex that runs back along the shortest path, all the way from V to the source vertex. So that parents attributes or pi attributes will tell us how to how to draw the shortest path in the graph. Okay. And the result is something like similar to a BFS tree. We call it a shortest path tree. Okay, but a slight difference is that now in the shortest path tree, the values of each node is not the number of edges, but the total weights of edges along the way. Okay, so that is how we represent a shortest path in a graph. All right, so next we're going to enter the detailed methods of how to compute the shortest path in a graph. So we'll first introduce a basic relaxation procedure or relaxation method. So this will be the basic or primitive operation that we will use to implement the two algorithms here. Okay, so the two complete algorithms are first Bellman-Ford algorithm and second Dijkstra's algorithm. Okay, so but they all they are all based on the primitive operations of so-called relaxation on the graph. Okay, so what is relaxation? It is a technique that basically all shortest path algorithms will use. So for each vertex in the graph, we maintain an attribute v dot d. Okay, so it is similar to the concept in BFS, right? So this property or attribute d, in this case, is an upper bound on the weight of a shortest path from the source to V. Okay, so the D is some upper bound, it is some quantity. It is not yet the shortest path. Okay, it is some quantity that is bigger than the shortest path. Okay, which we don't know yet. Okay, and we called V dot D a shortest path estimate. So it is currently just an estimate. It is not the accurate shortest path weight. So we can initialize all the D's with this procedure called initialize single source with the graph G and the source vertex as input. Okay, so it's basically a for loop that goes through all the vertices and initialize the D property to infinity, and then the pi, the parents, attribute to none. Okay, and then a special case is for the source vertex, and we make the D property, the D attribute, to be 0. Okay, because this is where we start. So the whole procedure is just in initialization. It does one thing, but just in initialization. Okay, so the process of relaxing. Okay, so relaxing or relaxation is a process or is an operation done on an edge. Okay, we can apply relaxation on an edge from U to V. So this process will test whether we can improve the shortest path to V. Okay, found so far by going through U. Okay, so it is a process that tests whether we can improve the D of V if we go through U. And if so, we'll update the V dot D and the parent node of V. Okay, so basically it will examine whether the shortest path from the source to V can be improved if we include the edge from U to V into that shortest path. And if so, then we should set the new value for the d of v, and then set the parent of v to u, right? Because u and v, if we include the u to v as part of the shortest path, then u becomes the parent, direct parent of v. Okay, so let's further look at how the relaxation procedures can be defined. So a relaxation step may decrease the value of the shortest path estimate v dot d and updates v's predecessor attributes v dot pi, okay, or parents property, parent attributes. Okay, and here's how the relax procedure is defined. So it takes input two vertices, u and v, and the weight table. So weight contains all the weights within the graph. So it's just one if condition, if statements. If the current d attribute is greater than the d attribute of u plus the weights between u and v, then we should update the d of v to be this new candidate, to be this new value, which is the d of u plus the weight of u between u and v. And then we update the pi attributes to be of v to be u. Okay, so it basically compares two values, which is the old d of v and the new candidate, which is the d of u plus the edge between u and v. So if that new candidate is smaller, then that means our shortest path from the source to v should include the edge between u and v. Okay, so in that case, we should update the values of d and the pi of v. And if that condition is not satisfied, which means if we include u, that doesn't improve the shortest path estimates, then we should not update the d of v or the pi of v. Okay, so essentially, any shortest path algorithm will need to call the initialize single source first to initialize all the d's and pi's, and then they will repeatedly call the relax on edges. Okay, so the nature of all shortest path algorithms are no more than these two steps. So basically, we'll first initialize all the d's and pi's, and then we just repeatedly call relax. The difference resides in how the relaxes are called and how the orders of edges are decided. Okay, and so relaxation is the only means by which shortest path estimates and predecessor, which is the d's and the pi's, are changed. Okay, so only in the relax procedure will be able to change the d and pi's for the vertices. Okay, so the most algorithms, they differ in how many times they relax each edge and the order in which we relax edges. So in this lecture we focus on Bellman-Ford and Dijkstra's, so they are different in terms of the order in which they relax edges. Okay, so with regarding the relax procedures and the properties of shortest paths, there are some interesting theorems or properties that we may need in the design of algorithms. Okay, so first of all, it is the triangle inequality. So it basically says for any edge, we must have that the delta of v, the delta is the shortest path weight, so it is the theoretical lower point, the lowest point, the theoretical or lower bound, the theoretically shortest path between S and V. So the shortest path weight between S and V should be smaller or equal to the shortest path between S and U plus the edge between U and V. So it basically says that if the shortest path between S and V should no bigger than the shortest path between S and U plus the edge. Okay, so that is a straightforward theorem, right? Because if that one is smaller, so if delta between S and U plus the weight between U and V is smaller, then the delta between S and V should not be the original value. It should be just that path, right? So the second property is upper bound property, okay? And it says we always have that the estimates of the shortest path, the D, remember that we called the D to be the shortest path estimate. It is just a upper bound, okay? So it's always greater than the theoretical optimal shortest path weight for all vertices, okay? And once the estimate achieves or reaches the theoretical optimal value, delta, then it will never change. Okay, so within the algorithm of finding the shortest path, once we relax all the edges repeatedly, so once for one vertex it reaches the theoretical lower bound or theoretical optimal value, optimal shortest path weights, then it will never go up again. Okay, that's the upper bound property. So that means once we reach the lowest points, we should update it no more. Okay. So another property is called no path property. So if there's no path from S to V, then we always have the D to be infinity, right? That's a straightforward property. And another property is path relaxation property. Okay, so this is a useful property. So assume that the path from V0 to V1, blah, 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 to Vk is the shortest path from V0 to Vk. So we assume that V0 is our source vertex. So, and we relax the edges along P in such an order. So we relax the edge from V0 to V1 first, and then V1 to V2, and then V2 to V3, and we relax Vk minus 1 to Vk. So if we relax edges in such an order, then the result is that the resulting D attributes of Vk will be the delta between S and Vk. So it will be the actual shortest path weight after we relax all the edges in such an order. Okay, and the assumption is that the path is the shortest path. P is itself the shortest path. So this property will hold regardless of any other relaxation steps that occur, even if they are intermixed. So that means even if we intermix other passes between these passes, as long as we keep the order unchanged, as long as we relax V0 to V1 before V1 to V2 and before V2 to V3. Okay, and the last property is called convergence property. So it says if the path from S to U and then plus the edge from U to V is a shortest path for some vertex U and V, and if the D property of U is already the delta, okay, anytime prior to relaxing U and V, and then the D property of V will be the delta at all times afterwards. Okay, so if before relaxing u and v, the theoretical optimal shortest path of u is already found, then after the edge from u to v is relaxed, then the shortest path estimate of v is also reaches its optimal lowest smallest also reaches the optimal shortest path value, shortest path weight. That's so-called convergence property. So using these properties and the relaxation procedure defined, we will now look at how a shortest path procedure and shortest path algorithm can be implemented. So we'll use Bellman-Ford algorithm as our first example. Now let's look at the Bellman-Ford algorithm. So Bellman-Ford algorithm solves the single source shortest path problem in the general cases, and the edge weights could be negative. So given a weighted directed graph and our source vertex S and the weight function as well, so the algorithm will return a Boolean value, and that Boolean value, which is true or false, indicates whether or not there is a negative weight cycle, okay, that is reachable from the source. So if there is a negative weight cycle, then the algorithm will indicate that no such a solution exists. If there's no such a negative weight cycle, then the algorithm will produce the shortest path and their weights. Okay, so as we have talked about this previously, the negative weight, so we assume that, so we already know that the shortest path should not contain any negative weight cycle nor positive weight cycles. Okay, so the Bellman-Ford. So here's what the Bellman-Ford procedure look like implemented with our pseudocode. Okay, so at line 1, it's just the initialization step which we already implemented. So this initializing single source will initialize all the D attributes and the pi attributes to all the vertices. Okay, so it's basically a loop over all the vertices. And from line 2 to line 4, it's a nested for loop. So if we look at the outer for loop, right, this for loop, it makes v minus 1 passes, right? It let I iterate over 1 to v minus 1. Okay, it makes that many passes over the edges of the graph, and for one within each iteration step or within each pass of this outer for loop, there is one inner for loop. Okay, this inner for loop from line 3 to line 4, which will relax each edge within the graph once. Okay, so let me say this again. So we have two for loops. In the outer for loop, it makes v minus 1 passes. Okay, so at this point, we don't care about why this is the case, why we use v minus 1. But we will show later that this works. And at line 3, at line 4 means that at each pass we will relax each edge, right? We iterate over all the edges in the graph, and we relax each edge once. Okay, so that's what line 2 to line 4 does. So after that is done, and then we go to line 5 to line 7, we use another for loop to check whether there is, right, a negative weight cycle, right? So if this is the case, if say for any edge we found that the D property, the D attribute of V is greater than the U property, the D property of U plus the weight of the edge from U to V, then we return false, which indicates that we cannot find a solution because there is a negative weight cycle in it. Okay. Otherwise, we'll return true, which means the algorithm works. Okay. So I guess it's easier to understand how this algorithm works using simple examples here. Okay, so the code is shown here, and we use a simple directed weighted graph in which there are negative weights. So first of all, it's the initialization, right? So the initialize single source function procedure will initialize all the d values into infinity except for the source vertex, and also we initialize all the parents attributes, pi attributes into none as well. Okay, so here's one thing about the algorithm. For each edge, we use a for loop from line 3 to line 4. We use a for loop to iterate over all edges. So we will just use an arbitrary order that the edges are relaxed. So within each pass, we assume that the for loop over line 3 to line 4 will iterate over the edges in such an order. So we will go through edge tx, and then ty, and then tz, and then xt, yx, yz, zx, zs, st, sy. So this is a totally arbitrary order. So you can always use a different order. So here we just want to make sure that within each pass, the order in which all the edges are relaxed remain the same, so that it's easier for our analysis. Okay, so now within the first pass of the outer for loop at line 2, we assume that each pass will relax the edges in such an order. Okay, so the edge from t to x will be the first one to be relaxed. Okay, so the edge tx. So I listed the pseudocode for relax procedure here. So the relax will be done if the d attribute of v is greater than the d of u plus the weight of the edge. Okay, so let's look at the case of tx. So currently the d attributes of both t and x are infinity, right? So the relax will not change anything because the infinity is not greater than infinity by the rules. Okay, so nothing will be changed, nothing will be updated. Okay, so that's what happened after we call relax on t and x. So similarly for ty, nothing will be changed as well. And for tz, xt, yx, all the way down to zs, because the source vertex and the destination vertex, they all have infinity as they are d attributes and a pi attribute, so nothing will be updated when the relax procedure is called. Okay, so the exception is here at edge st, right, which connects s to t. So when this edge is relaxed, the d attributes will be compared to the d attribute of s plus the weight of the edge, which is 6, right? Because the infinity is greater than 6, therefore the relax will make such changes because the if condition satisfies. Okay, so the d of t will be updated to 6, and the pi, which is the predecessor or parent vertex of t, will be set to s. Okay, and then when sy is relaxed, same change, the change will be made too, because the d of y is infinity, which is greater than the d of s plus the edge 7. Okay. So that's the results after the first pass of the outer for loop. Okay. So in this updated view of the graph, notice that the D attributes of vertex T and the vertex Y, they are updated, right, from infinity to the real numbers 6 and 7 here. And the edge ST and SY, they are also highlighted to the broader gray edges, because now they are in a predecessor relationship, or which means the pi of T is set to be S and the pi of Y to be S too. So that means the edge ST and SY, they are now in the Bradford, no, they are in the tree, in the final trees that represents the shortest path, or what we call the shortest path trees. Okay, so that's the first pass, and now there will be 3 more passes, right? Because in total we have 5 vertices in this graph. So according to the range of the for loop, we will let I range from 1 to the number of vertices minus 1, which is 1, 2, 3, 4. Right? So we have 3 more passes to go. Okay. So in the second pass, we assume that the inner for loop will follow the same order when relaxing all the edges. Okay. So this time, when we relax Tx, now the attributes of x will be updated, because now the d of t is no longer infinity. So when we do the comparison, the d of x is infinity, which is greater than the d of t plus the weight of the edge. So we will make a change by update the d of x and the pi of x. So the pi of x will be t. And for t, for the edge ty, however, because the y of d, the d of y is 7 and the d of t is 6, so the d of y is smaller than the d of t plus the edge, plus the weight of edge, which is 6 plus 8, which is greater than 7. So the if condition does not satisfy, so we will not make any changes when we relax ty. Okay, and for tz, this edge, okay, the original value of d is infinity, and now it's greater than the d of t plus the edge -4. So this time z of t will also be updated. Okay, and similarly, the edge yx will also be updated, and the rest of the edges will not be updated. Okay, so let's look at the results after the second pass. Now these two more edges, they are highlighted because the pi attributes of z and x, they are set. So so far that's what the current shortest path tree look like. Okay, and we have 2 more passes to go. So in the third pass, we found that there's only one edge. When we relax it, the d and the pi will be updated, and all the rest of the edges will make no change. Okay, so for xt, okay, the d of t is 6 and the d of x is 4, and 6 is greater than 4 plus -2. So we will relax this edge and make the changes by set the d of t to be 2 and the pi of t to be x. Okay, right? So after the updates, this original bold edge will be gone, because the parents or the predecessor of t is no longer s, but it follows to the it becomes x. So x will be the direct predecessor of t. So that means if you now look at the d property, which is the can estimate for the shortest path weight. So now that means if we go through this path from s to y, and from y to x, and then x to t, which gives you 7 minus 3 minus 2, which is 2. And that weight is smaller than a direct path from S to T. So that means the shortest path from S to T is this seemingly longer path. Okay. So that's after the third pass. So what if we go through the fourth pass, okay, and all these edges, they will not be updated, and only TZ will be updated when we relax the edge, okay. So the original D of Z is 2, and it's greater than the D of T plus the weight, which is -4. So the new D of Z will be -4, and the new parents or predecessor of Z will be T. Okay. So after the fourth pass, this will be the final graph, final view of the graph. Okay. So next, there will be line 5 to 8, which mainly examines whether there's negative weighted cycles in the graph. So we will basically check all the edges, right, and check if this condition is satisfied. If any one of these edges satisfy this condition, then the algorithm will return false. And fortunately for this graph, the Bellman-Ford will return true, which means that there's no negative weight cycles found, and the shortest passes for all the vertices, they are valid, and the highlighted edges here are the so-called shortest pass trees. Okay, so along this tree, we can find all the shortest pass weights of all the vertices. Okay, so the shortest pass from S to Y is this pass, and from S to X is SYX, and X to T, that is the shortest path for T, and from T to Z, that is the shortest path for Z. Okay, so that's how the Bellman-Ford algorithm runs on this simple example. Now let's quickly look at the running time of Bellman-Ford algorithms. So it's a quite straightforward analysis. So if we look at line 1, it's an initialization that iterates over all the edges. So it'll take big O of V times. Okay, and for line 2 to line 4, which is the main body of the relaxation, where the relaxation happens. So there are two for loops, right? The outer for loop will take big O of V time, because it iterates over all V minus 1 passes. And each inner for loop iterates over all the edges. So that means each inner for loop takes big O of E times. So in total, it's big O of V times E in total running time, right? That's quite straightforward nested for loop where you do the multiplication, right? And the rest of the code from line 5 to line 7, which is a one layer for loop that takes big O of E times. So in total, adding that up, the Bellman-Ford algorithm will run in big O of V times E times. Because when you compare these three terms, big O of V and E, V times E with big O of V and big O of E, this big O of V times E is a higher order term. So it is the most dominating term. Okay. And as for the correctness, so if you are curious about why this algorithm works, the textbook gives some a brief proof about the correctness of Bellman-Ford. So it basically uses the relaxation property that we have mentioned in slide 59, showing that if we relax all the edges in such an order, then it will be guaranteed that the D property, the D attribute of the final vertex will be the delta, which is the shortest path weight that we desire. Okay, but all we need to know is that Bellman-Ford is one of the algorithms that find the shortest path for all the vertices in the graph for us, and it is a correct algorithm, and it is quite easy to understand. We just make that many passes, and each pass we will relax each edge once, and the relax procedure or relax function is also have a very clear definition. Okay, so that's it so much for today's lecture, and in the next lecture we'll look at a special case of finding the shortest path in a special type of graph, which is the DAG, directed acyclic graph, and also we'll introduce another algorithm, which is the Dijkstra's algorithm.